Hello, everyone. My name is CJ, and I am the main author for this paper. So in this submission, I'm going to talk about this new network architecture conversion. But before going to talk about that with deep learning, it has gained a lot of momentum. The main reason why is that the performance or accuracy has performed really well. But the main issue is that it is considered as a black box. You send in the input as images or temporal sequence, then an output is provided. But in some scenarios like medical imaging or autonomous driving, you want to care why that decision was made because people's lives are on the line. So result-based analysis is not enough. And in the literature, there are different definitions for interpretability and explainability. So then in this scenario, we're going to be very concrete in the type of definitions that we want for those terms. Interpretability means understood by a human. Explainability means can be stated in a mathematical formal manner, such as an equation. So then here's one scenario to motivate the reason why we want interpretability and explainability. We have this dog. We train an animal classifier, and we send in all these images, and the classifier will say it's a dog. But then we take the same dog and put a shark suit, and let's see what happens. Will it classify it as a dog, a shark, or a pup? And this is why interpretability and explainability with deep networks is important to understand and probe inside to see why is it making these decisions. So in this scenario, we're going to take a recurrent neural network and convert it into our NeuroView version so that we can explain the classification with respect to all the hidden state units in a formal manner. So then we're going to concatenate all the hidden state units and have it as input to the linear classifier. So now we have the linear mapping between the time steps and the classes since we concatenate all the hidden states. So then the weights will show us positive or negative weight values for all the time steps for each of the classes. So then now that formal equation, y is equal to all the hidden states times the class weights that are being learned. So in this case, we're learning both the hidden state values and the class weights. So we have this explainability that a typical recurrent neural network cannot provide. And we're also going to have on-par performance. So then here is a diagram to represent what is our conversion. And in this case, we're just concatenating all the hidden state values into the linear classifier for it to do the prediction. With a typical one, all you have is the last hidden state. So you can see the major difference that we're doing. Yes, we're concatenating more parameters, but we need this for the explainability. And we do show great performance in the paper. We perform really well on 20 different time series classification data sets. We did have a small drop in accuracy for the movie review sentiment classification, but that was mainly due to the zero padding since we had variable length reviews. And also we performed really well on a video action recognition data set where we both had a convolutional neural net and a recurrent neural network grouped together. So we have spatial units and temporal units combined. So then when we train end to end, we can look at the linear classifier and look at the weights for each of the classes and inspect which time steps have the highest positive weight value and which one has a negative weight value. And there we can inspect and look back at the input data to see is it focusing on parts of the data that we wanted to look at. So here we can go back and forth and inspect and be able to explain, okay, we can see where it's making those decisions at these points.